Hey y'all, welcome to Science and Engineering at KSP. I'm your host Andy Leonard, and today we're going to talk about the patched conic approximation, and we're going to use it to finally break out of Kerbin orbit and get us to the moon. So the first thing we're going to talk about is the sphere of influence, and the sphere of influence is going to be pretty helpful in figuring out patched conics. The sphere of influence is basically this imaginary region in space around a planet or a moon, pretend that's Kerbin right there, where a spacecraft is only being acted upon by the planet in terms of gravitational forces. Now, we've talked a little bit about perturbations and stuff like that, but when you talk about things in terms of sphere of influence, you basically sidestep the whole problem of perturbations, and you just assume that any spacecraft in any orbit in this boundary is only going to be acted on by Kerbin. So here we have the moon, and the moon has a smaller sphere of influence. As we'll find out, the sphere of influence is proportional to mass. And so what patched conics is all about is basically taking an orbit from one sphere of influence to another, and then once you cross this boundary here from this sphere of influence into this one, your orbit's going to change somehow. The geometry is going to change, and you're going to have a different type of orbit, because of the different gravitational parameter and considerations like that. So how do we find the sphere of influence? Well, the radius of the sphere of influence is given by this equation. We take the semi-major axis and we multiply it by the mass of the planet or moon and divide it by the mass of the sun or the planet the moon is orbiting. And we take that and we raise it to the 2/5 power. So for Kerbin, and that's going to give us a sphere of influence radius of 84,159,107 meters. The radius of the sphere of influence of the moon is 2,429,571 meters. So when we're within about 2,000 kilometers of the moon, we're going to switch over into the moon's sphere of influence. All right, so for beginning a patched conic analysis, we need to draw a little schematic of Kerbin and the moon, and we need to design a trajectory that will get us from our initial orbit around Kerbin and bring us out and cross the moon's sphere of influence. So with our initial radius and initial velocity, we can, and our initial flight path angle, but for the example we'll assume a flight path angle of 0, meaning we'll be burning at periaps. And so with that information, we can figure out our radius from Kerbin to the patch condition here. And we need this little angle lambda 1 here, which is the angle between the line joining Kerbin and the moon and the point where we enter. And if we zoom in and take a closer look at the patch condition, we can see how our velocity is going to change. So this Vm here is the velocity of the moon as it's orbiting Kerbin. And then if we come into the patch condition with this initial velocity V1, what we do as soon as we cross that boundary is we subtract the moon's velocity. So we end up with our velocity vector pointing this way. And this angle epsilon 2 here is the angle that we're pointing at with respect to the moon. So in epsilon 2 of 0, we would be pointing directly at the moon and aiming straight for it. I know a lot of this seems arbitrary right now, like, you know, what do we do with this phi1, this gamma 1, this phi1 minus gamma 1? So let's just jump straight into an example. Okay, so first things first, we need to find out what our transfer orbit is going to look like. We're going to start off in about 100 kilometer altitude circular orbit, so that means our radius is going to be 700 kilometers. And what we want to do is we want to raise our apoapse and bring it out to about the orbital path of the moon here. So we want our transfer orbit to look something like this with the apoapse out here. But let's not use the semi-major axis of the moon as our apoapse. Let's add in 240 kilometers. So we'll have an apoapse distance of 12,240 kilometers. Now I added in 200 kilometers because that's the radius of the moon, and I added in 40 kilometers because we don't want to hit the surface. And we won't end up hitting the surface with this, but it's just kind of a random number. You have you have a considerable bit of leeway when you're choosing your apoapse distance for a patched conic trajectory. So anyway, that means that our semi-major axis is going to be equal to 12,240 kilometers plus 700 kilometers over 2. And that gives us a semi-major axis of 6,470,000 meters. Now our velocity at periapse after we've created this transfer orbit is going to be given by mu times 2 over r naught, and we'll call r naught the 700 kilometer distance here, minus 1 over a. And that's going to be equal to 3,089.4 meters per second. And now what we want to do is we want to find some of the other parameters of this transfer orbit, like the specific mechanical energy and the specific angular momentum. So for the energy, we find the energy is equal to periapse velocity squared over 2 minus mu over the initial radius. And we find that we have an energy of negative 272,946.677 joules per kilogram. And for our angular momentum, since we don't have a flight path angle here, we're burning at periapse, our angular momentum is going to be given by RV. And that is going to be 2,162,058,580,000, meters squared per second. So now that we have this information, let's redraw the schematic we saw a minute ago, just to remind ourselves of what's going on here. We have this is the distance between Kerbin and the moon, and we have the sphere of influence here, and we have our new radius that's going to be created by our transfer orbit R1. So we have to pick this value of lambda 1 here. That's going to be something that we're free to choose, and we'll just pick lambda 1 equals 40 degrees. Then we can find R1 using the law of cosines, where R1 is equal to d squared plus the sphere of influence around the moon squared minus 2 times d times the sphere of influence radius times the cosine of lambda 1. And we take the square root of all of that. And when we do that, we find that our radius with respect to Kerbin when we're about to enter the moon sphere of influence is 10,258,410 meters. And then we can find the velocity by taking the square root of 2 times the energy of the orbit plus the gravitational parameter of Kerbin over the radius we just found. And when we do that, we find that our velocity there at the entrance to the sphere of influence is 377.67 meters per second. Now let's find the flight path angle as we're entering the sphere of influence. And the flight path angle is given by the arc cosine of the angular momentum over the radius and velocity. And when we do that, we find that this angle is going to be 56.07 degrees. Now let's figure out that angle gamma 1. Gamma 1 is just the arc sine of the sphere of influence radius of the moon over the radius that we have when we're entering the sphere of influence times the sine of that angle lambda 1. And doing all that, we get that we have 8.756 degrees. And let's go ahead and let's convert this to radians real quick because we'll need it in radians in a second. This is going to be 0.1528 radians. Now we need our true anomalies for this orbit about Kerbin. So we can say that our initial true anomaly was 0, right? Because we're firing at apoaps. We fired at apoaps and raised our periaps directly above us. But for our true anomaly at arrival to the sphere of influence, we find that by taking the arc cosine of the semilattice rectum minus R1 over R1E. Now, let me check here. I don't think we did the semilattice rectum or the eccentricity. That's okay. We can do it right here. The semilattice rectum is going to be equal to the specific angular momentum squared over mu. And that's P, and that equals 1,324,000 meters. And the eccentricity here is going to be given to us by 1 minus P over A. We'll take the square root of that, and that'll give us an eccentricity of 0.8918. So now that we know our semilattice rectum and our eccentricity, we plug them into this equation here, and this is not phi naught, or theta naught, this is theta 1, and theta 1 is going to be 167.57 degrees, or 2.9246 radians. What this means is that starting here, if we fire here and we create our periaps, with respect to Kerbin, we'll be kind of out here, right? And so not quite 180 degrees around from where we started, but pretty close. And now we need to know the time of flight, because we need to know when to perform the burn to create the transfer orbit and get us out there, because it doesn't matter how on target we are as far as the apoaps is concerned if it's not in the right position, right? So in order to talk about this, we need to introduce this new parameter called the eccentric anomaly, and it is represented by the letter capital E. And the capital E is equal to the arc cosine of the eccentricity plus cosine of the true anomaly over 1 plus eccentricity cosine true anomaly. Now, if we have a true anomaly of 0, this all kind of cancels out, and this is 0. So E0 is 0. E1, if we plug in this value of true anomaly here, we get that our eccentric anomaly is equal to 131.04 degrees, or 2.287 radians. And then we can get our time of flight by taking the square root of a cubed over mu of Kerbin and multiplying it by eccentric anomaly minus E sine eccentric anomaly minus the initial eccentric anomaly minus E sine initial eccentric anomaly. And of course we didn't really need this second term here because this all cancels out. And when we do this math, we find that our time of flight is going to be 14,137.43 seconds. And what are we going to do with this information? Well, we have to multiply it by the angular speed of the moon, and we find the angular speed of the moon by taking the period, which is equal to 138,984 seconds, and dividing it into 2 pi. So we basically do 2 pi over t equals the angular velocity of the moon, which is equal to 4.5208 times 10 to the negative 5 radians per second. And now finally we're ready to compute the phase angle that we need on departure. So that's gamma naught, and that's going to be equal to theta 1 minus theta naught minus gamma 1 minus omega n times time of flight. Remembering to keep everything in radians, when we do all that, we get an angle of 2.13267 radians, and that is equal to 108 and 22.19 degrees. So that's going to be the angle that we're behind the moon by when we fire our engines and kick up our apoaps and intercept the moon. Now let's move on and talk about some conditions at the patch condition. Again, using the law of cosines, we find that our velocity with respect to the moon, v2 from that schematic we had earlier, is going to be equal to v1 plus the velocity of the moon, both squared, minus 2 times v1 times vm times the cosine of that weird angle, that phi1 minus gamma 1. And we take the square root of all of that business. And when we do that, we get that our v2, by the way, yeah, vm, if we do 2 pi d over t, we get that the velocity of the moon is 542.5 meters per second. So plugging that all in, we get that our velocity just after crossing over into the moon's sphere of influence is going to be equal to 398.9 meters per second. And we can find that angle epsilon 2 by taking the arcsine of the moon velocity over velocity just after entry times the cosine of that angle lambda 1, and we subtract the geocentric velocity over the moon entry velocity, and we multiply that by the cosine of lambda 1 plus gamma 1 minus phi 1. And doing all that, we get that our entry angle here is going to be 7.28 degrees. And now we're finally ready to move on and talk about the parameters of our final orbit about the moon. We can find the specific mechanical energy associated with the orbit by taking v2 squared over 2 minus the gravitational parameter of the moon over r2, which is just going to be the sphere of influence radius. And the gravitational parameter of the moon, mu sub m, is 6.51384 times 10 to the 10. And plugging that all in, we find that our specific mechanical energy is 52,749.9 joules per kilogram. And that should look weird to you. We've never seen that before. We've never seen a positive value of the specific mechanical energy. So there's going to be something screwy with this orbit. And we find the angular momentum by the radius times velocity times sine of that epsilon 2 angle. It's a weird looking epsilon, but we'll take it. And the specific angular momentum is 122,809,846.9. And we find the semilattice rectum by squaring that and dividing it by the gravitational parameter, and we find that the semilattice rectum is 231,541 meters. And finally, we're going to get the eccentricity. And the eccentricity is the square root of 1 plus 2 times energy times h squared over mu squared. And when we do all that, we get an eccentricity of 1.1726. So we know that the orbit is no longer an ellipse, and that's what the positive value for the specific mechanical energy translates into. And along with this value for the eccentricity here, we know that we don't have a closed orbit around the moon. No, we have an open orbit. So unless we apply some delta V to close the orbit, we're just going to shoot out and break outside of the sphere of influence once again, and we'll be in Kerbin's influence. And finally, we find our periapse radius by dividing the semilattice rectum by 1 plus e, and we find something kind of funny. Our periapse radius is 106,573 meters. And remember when I said that the radius of the moon was 200 kilometers? So yeah, we're about halfway in between the center of the moon and the surface of the moon. So we're going to definitely crash into the moon unless we apply some delta V and raise our periapse. But you know, that's pretty trivial to do. As long as you're far away from the moon, you can just get away with applying very minimal delta V to perform corrections. And there you have it. That is the patched conic approximation for a lunar approach trajectory. Let's switch over to KSP and see how we did. All right, so here's Jeb in his 100-kilometer circular orbit, and we are going to try and get out here to the moon without planning a maneuver. We've set the moon as our target so we can get our phase angle information. We've killed just about all of our relative inclination. We know we need to burn until this says 3,089.4 meters per second, and we want a phase angle of 122.19 degrees, but we're going to want to burn a little bit earlier, so that means we're going to burn at about 125 degrees. All right, so we're coming up on it. We're set to burn prograde. Just waiting for the magic number here, and that's close enough. Let's do it. We're very close, so we're just going to bump up our velocity just a tiny bit. And we're there. So let's see how we did. Let's go over to map view. And yeah, that looks like an impact trajectory right there. So we're going to focus our view on the moon. And yeah, we will, our periapse is well below the surface of the moon. So we will impact it. Don't worry, we're not going to let Jeb hit the surface, but what we are going to do is we're going to warp ahead to the patch point here, and we're going to see how the numbers check out compared to what we calculated. So yeah, we're almost at the patch point, and our velocity is a little bit higher than we predicted. It's 413.8 meters per second, and that's not too bad. Remember, the value we calculated was 377.67 meters per second. So, I mean, it's a little bit off. And we just switched over there. And let's take a look. Our velocity here is 425 meters per second, and our velocity just after the patch condition was 398.9 meters per second. So a little bit higher in both cases, probably due to slight phase angle errors and very small delta V differences, but we got pretty close, and we just showed that the patched conic approximation is a pretty good way to plan your missions. And obviously there's more to it than what we've gone over. We need to apply it for return trajectories, and later on we'll get into interplanetary trajectories, but that's for another episode. Make sure you tune in next week. We are going to be doing a bit of a special episode. We're going to tie everything together, and we are going to math our way through an entire moon mission, from designing the rocket to the trajectory to planning our maneuvers and everything. And I'm pretty excited to do it and celebrate 10 episodes. Well, I think that's it for this week. Thank you for watching. I hope you had fun watching it. I had fun making it. See you next week.